This is 7.7 of Algebra. So we're going to continue talking about exponential functions, but we're going to look at a couple specific cases. So this is called exponential growth, okay? You can see in the picture, this is when you start small and get big, okay? So here's our equation. The A is our initial amount, how much you start with, okay? And our B is our base, and that's our growth factor. So to figure out our growth factor, though, we're not just going to take the number out of our equations, or out of our problem. So let's say the problem is saying that every year the population of squirrels increases by 50%. Okay? You're not just going to plug in 50% for B. Okay? Because what we're talking about is we're talking about taking how many squirrels we have now and adding 50% more. Okay? So we already need our whole and add 50% more. So what we do is that we add 1. So 1 plus the percent rate of change. Okay, and we put that in as a decimal. So if it was growing by 50%, we would put in 1.5. Not just 0.5, we put in 1.5. So, suppose that in 1985 there were 285 cell phone subscribers in a small town. The number of subscribers increased by 75% each year after 1985. How many cell phone subscribers were in the small town in 1994? So, y equals a times b to the x. Remember, a is how much we're starting with. So, in 1985, there were 285 cell phone subscribers. So, we started with 285. And now we need to figure out what b is. Okay? So, it says that it's increasing by 75% each year. So we need to write 75% as a decimal, okay? That's 0.75. If you're not sure what it is, here's where our decimal started, right? You need to move it 2 times to the left. 1, 2. So 0.75. And then, since it's a growth, I need to do 1 plus 0.75, which gives us 1.75. So I plug in 1.75 for B. And that's to the x. So here's my equation. The last thing they ask is how many cell phone subscribers were in the small town in 1994. Okay, so we need to think about where we started. What was our year 0 essentially? So 1985 was our year 0. So I'm not going to plug in 1994 for x. What I need to do is see how many years after was that. So you can either count it out with saying 1985 was year 0, so then 1986 is year 1, 1987 is year 2, that sort of thing. Or what you can do is you can do 1994 minus 1985, which gives us 9. So it's year 9, and that's what I need to plug in. So y equals 285 times 1.75 to the 9th. So to solve this, we need to take care of our exponent first. So we're going to do 1.75 to the 9th power. So this is y equals 285 times about 153.9. And then 153.9 times 285 gives us 43,800, and we'll round it up to 62. So 43,862 cell phone subscribers. And that would be our answer. Okay, now we're going to talk about compound interest. So if you keep money in a savings account, you earn interest just by leaving the money in there. Okay? So this is an example of exponential growth. As you leave money in your bank account, it grows. So here's our equation, and here's the description of everything that the variables stand for. Okay, so our balance, A stands for the balance, how much money we have in there at the end. P is the principal, the initial deposit. Also, another way you can say that is how much money you put into it. Okay. R is the annual interest rate, and you need to make that a decimal. So remember, move the decimal point to the left. N is the number of times interest is compounded per year. So sometimes it'll say compounded annually. If you think about your annual Christmas party, right, that happens once a year. So if we're talking about compounding annually, that's once a year. Sometimes you'll see quarterly, that's 4 times. Sometimes you'll see monthly, that's 12 times a year. And then finally, T is the time in years. So let's try using that. Let's write our equation. A equals P times 1 plus R over N to the NT. Okay, so we're going to use our problem up here and just change one of the numbers. So, suppose that when your friend was born, your friend's parents deposited $2,000 in an account paying 4.5% interest, and theirs was compounded quarterly. We're going to do our problem down here, which is compounded monthly. So, monthly. What will the account balance be after 18 years? Okay, so how much we put in, that's our P, the 2,000. This is our rate, but we need to change it into a decimal. So if we have 4.5%, we move the decimal 2 times. So R is equal to 0.045. Compounded monthly tells us that our N is 12, and we want our T to be 18. So A equals P times 1 plus R over N to the NT. So A is equal to, we put in $2,000, 1 plus, on top is 0.045 over 12. And this is to the 12 times 18. So the first thing I'm going to do is that I'm going to divide this right here. Okay, so on my calculator, I'm going to do 0.045 divided by 12. If you can help it and not round, that's best. You're going to get the closest answer. Or you need to round with a couple decimal points, okay? This comes out to be 0.00375. And while we're at it, why don't we simplify these that exponent up there? 12 times 18 gives us 216. So this is A equals 2,000 times, and now I'm going to add these right here. So 1.00375 to the 216. So now I need to take care of this exponent, so I'm going to do that 1 point, all of that, to the 216th. So 1.00375 to the 216th gives us, well, we've got our 2,000 up front, times 2.245, we'll go like that. And then 2.245 times 2,000 gives us $4,490. Okay, and our last kind of problem, exponential decay. Alright, so this is similar to exponential growth, okay, but when we were talking about exponential growth, just like it sounds, we're talking about it increasing, right? It was started small and got big. This one is going to start big and get small. So, same equation. A still stands for our initial amount, how much we start with. Our base is the decay factor, and the decay factor is a little bit different. You're going to do 1 minus the percent rate of change. Okay, so when we were talking about exponential growth, we're doing 1 plus. Now we're going to do 1 minus. So, the kilopascal is a unit of measure for atmospheric pressure. The atmospheric pressure at sea level is about 101 kilopascals. For every 1,000 meter increase in altitude, the pressure decreases about 11.5%. And then we're going to do our problem down here saying what is the atmospheric pressure at an altitude of 5,000 meters. So we've got our equation, y equals a times b to the x. A is how much we started with. So at sea level, which is where we're starting, that's at the 0 meters high, kind of. We're at 101 kilopascals, so 101 goes in. Now we need to figure out what our B is. This is exponential decay, so we need to take our percent. So our percent is 11.5%. First thing we need to do is we need to write that as a decimal. So I'm going to move this once, twice, so I get 0.115. And that's not the thing I plug in. Remember, exponential decay, we need to do 1 minus that. So I'm going to do 1 minus 0.115, and we get 0.885. This is what goes in for B. So 0.885 to the x. And then we want to know what is the atmospheric pressure at an altitude of 5,000 meters. I'm not going to plug in 5,000 for x. That would be a really big number. Or really small. But what I'm going to do is, if you look in our problem, it says for every 1,000 meter increase in altitude. So this isn't going up by 1. Doesn't change every 1 meter you go up. It changes by every 1,000 meter. Okay? So if I'm going up to a 5,000, I go up 1,000, 2,000, 3,000, 4,000, 5,000. That was 5 times. So I'm going to plug in 5 for x. So y is equal to 101 times 0.885 to the 5th. So the first thing I need to do is take care of that exponent. So I need to do 0.885 to the 5th. So this is 101 times, I get about 0.543. Okay, and then if I do 101 times 0.543, we get that the atmospheric pressure is about 54.8 kilopascals. And there you go, there's your homework.